Hello and welcome to the lecture on the motion of satellites. Okay, so we're going to use force and energy to understand satellites in orbit. Okay, so we're going to understand that the motion of satellites can be understood through the conservation of energy using universal gravitational potential energy combined with uniform circular motion and the associated centripetal acceleration when used with Newton's second law. What I mean by that is we're really going to be employing the universal gravitational potential energy equation that we saw in the very last lecture. So we're definitely building on that idea and putting it to use. And we're going to talk a bit about elliptical orbits, but only a little. Okay? All right, so let's define a satellite. All right, it's an object that is natural or artificial that is in orbit around a celestial body. Satellite orbits can be circular or elliptical. So circular or elliptical. Okay? Satellites must have a large enough velocity so that they can complete a curved trajectory around a celestial body. Because otherwise they would be in a projectile motion in the traditional sense, like a parabola, and they'd eventually hit the ground, right? So, but it has to be steep enough that they never hit the ground, their motion, okay? Okay, so we're now consider a few key equations. All right, our first one is the potential energy of a satellite, okay? So this is the gravitational potential energy of the satellite. Okay, so it takes the form of universal gravitational potential energy, right? It's inversely proportional to the distance from the center of mass of the planet. It is always negative, and it asymptotically approaches 0 joules at an infinite distance away from the planet, okay? These are all the same things we've seen for universal gravitational potential energy before. Okay? R is the distance from the center of the planet. The actual altitude above the planet would be h, as we see here. Okay? The difference between the radius of the planet, uppercase R, and the orbital radius of the satellite is h, which is the altitude, right? The term that describes the vertical distance above the ground. Right? And here's our satellite, this little box. And we can see there's only a single force acting on it, the gravitational force. And we know from before, talking about circular motion, that that gravitational force is a form of a centripetal force. And thus the mass times the satellite is the mass of the satellite times centripetal acceleration is that force. Okay? And so here we have the gravitational force, universal gravity, okay, set equal to mass times centripetal acceleration. Because of course here in parentheses, this is centripetal acceleration, okay? So this is putting use to the other recent formula we saw, which is the universal force equation for gravity. Okay, so then we can combine this to describe the kinetic energy of the satellite, okay? So if we consider the net force acting on a satellite, then we can see that the velocity squared is equal to gravitational constant times the mass of the planet, uppercase M, divided by the distance between the satellite and the center of the planet, r. You see it? All I did was took this equation, Newton's second law, for this situation of gravity and circular motion, and solve for v. That's all this is. But that has the very interesting effect of then being able to take the definition of kinetic energy, 1/2 mv squared, and replacing v squared with this expression, which looks nothing like v squared, right? Because it's gravity times mass over radius, but has the same units, meters squared over second squared, and describes the system of the satellite. And the neat thing about that is then we can express the kinetic energy in the satellite like this. And notice now it takes the same form as the potential energy. These are now like terms, okay? That's actually really helpful, really elegant, simple way of thinking about the energy in a satellite. And we were able to get there through just Newton's second law, an understanding of circular motion, and our recent definitions of universal gravitational force, and something that's derived from it using calculus, which is universal gravitational potential energy. Okay? All right, and then we can obviously solve for the velocity by taking the square root of both sides. And we have a helpful expression of always being able to quantify the velocity of a satellite in orbit around a particular planet at a particular distance. So you can think of this as satellite velocity as a function of distance from the center of that planet. All right, so if you had a satellite that was you were told it was a certain altitude, then you could easily find its velocity this way. And then, as I mentioned before, because the kinetic energy and gravitational potential energy are now expressed as like terms, in other words, they have the same denominator, right? We can then express total mechanical energy, E sub satellite, as kinetic plus potential, and it just becomes this. See? Now, there's a couple fascinating things. First of all, this is a very simple expression of total energy of a system, so especially a system as complex as a satellite, so it's a great simplification. And furthermore, it's also always negative, just like gravitational potential energy. But that makes sense if you consider the idea that we recently introduced, which was escape velocity, because if a satellite is in orbit, it's still trapped in the gravitational well that is the planet. It hasn't escaped, it hasn't achieved escape velocity. And since it's still in the well, its total energy must be zero. Well, excuse me, less than zero. It has to be negative because it's still in the well. It still has a total energy that is less than zero. Okay? It will only escape if it achieves zero. Okay? And it could, have a total energy greater than zero if it's on a permanent trajectory that is accelerating away from the planet, for example. Okay? But a satellite certainly isn't. A satellite is still very much trapped. Okay? Even though, it's above the atmosphere and is in motion. And an interesting similar expression to the total energy of a circular orbit is the total energy of an elliptical orbit. And what's nice about it, and this is really the way we're going to use it, we're not going to kind of get too much into ellipses. I'm not going to cover Kepler's 3 laws, in particular Kepler's first law that really defines exactly how we should think about an ellipse. Instead, we're just going to take one quick view of it, and all I want you to know is that you can replace the radius with the semi-major axis of the elliptical orbit, but the form is otherwise identical. What's interesting about this is that then that can allow for a variation in the period of the orbit. So changing from a circular orbit to an elliptical orbit can change the period of the orbit. You'll see that in the final example. Okay? All right, well, here are our key formulas. Let's get to some practice. All right, so in practice problem number 1, we're going to consider a satellite around Venus. Okay, so we're going to have a geosynchronous satellite, which is one that stays above a fixed point above the surface of a planet. These types of satellites are important for communication networks. However, for planets with very slow axial rotation, in other words, a very long day, they may present a problem. What altitude would a geosynchronous satellite need to be located above the surface of Venus's equator? Okay, so Venus is a lot like Earth in size, but unlike Earth, it doesn't have a day that is 24 hours long. Instead, it has a day that is about 1 Earth year long. So it has a very, very, very slow rotation period. And that means that it has some very different dynamics than here on Earth. So let's think about in terms of what it means to solve for the altitude of a geosynchronous satellite. Okay, because a geosynchronous satellite, in order to remain fixed above a certain point on the equator of a planet, such as Earth, all right, or Mars, or in this case Venus, is it has to have an orbital period that is equal to the day of that planet. So if you imagine a planet that's rotating at a certain rate, and then you put a satellite out here, we need the satellite to take just as much time to go around as a planet takes. So we need these two processes, these two arcs, to be lockstep. Okay? So the time it takes for them to complete a circle must be the same. Now, of course, the satellite is completing a much larger circle than, say, the surface of the world, but they still need to be moving at the same rate. Okay? All right. I should say, the same angular rate, because obviously the velocity, the actual translational rate of the satellite will be much greater because it's completing a much larger circle at the same amount of time. Okay? So from the sum of forces, we'll use Newton's second law here. We're just setting universal gravitational force equal to mass times centripetal acceleration, and then we're solving for the velocity in terms of these variables, okay? But before we do so, I should say, over here, we're expressing the velocity for uniform circular motion, because by definition, velocity is distance over time, if it's constant. Well, velocity is constant in magnitude for uniform circular motion. It's constant speed motion, okay? Not constant direction, but definitely constant speed. So that means that for the velocity of a satellite, it's simply the circumference over the period, okay? and that's what we're showing here. Circumference 2 pi r over the period of the satellite. And we know that the period of satellite has to be the same as the period of Venus because this is a geosynchronous satellite. I'll do an example for another type of satellite where that's definitely not the case. Most satellites are not geosynchronous. For example, the International Space Station, a well-known, famous satellite, has a orbital period that is only 90 minutes, much, much shorter than 24 hours. Okay, so then we're going to solve for the period of the satellite, TS, okay? All right, see that? See, I just took this expression, I substituted this in, and then solved for the period of the satellite, okay? By just substituting and solving, okay? And then I'm going to set this equal to the period of Venus and square both sides, and then solve for the radius of the satellite's orbit, okay? Because everything else is known. Mass of Venus is known, period of Venus is known. Our only unknown is the orbital radius of the satellite. And since it's cubed, and it's cubed because here we had an r squared and an r, so we actually solved for TS within the substitution of V, it became, of course, r to the third power, all right? And then when we plug in our values, and remember to raise it to the 1/3 power, which is the same as taking a cube root, then we end up with an orbital radius for this geosynchronous Venusian satellite as 9.42 times 10 to the 8 meters. Okay? So in other words, that's 942 million meters, or 942,000 kilometers. That's actually really far. Okay? To put that in perspective, the radius of Venus is about 6,000 kilometers. And here we're talking about 942,000 kilometers. That's so high above the planet that the planet would be a distant dot, a faint dot from the view of the satellite. Okay? Here, since we were interested in the altitude, we'll go ahead and subtract the number, right? Which isn't going to have a very big bearing, right? Look, it only changes these decimal places, right? We still have it to the 8th power, right? Because it is so much further. In fact, it is 155 times the radius of the planet above the planet, right? So if this was the planet, we need something that's 150 times bigger, right? So that maybe, more dramatic than that, okay, for the orbit. Okay, and for comparison to Earth, a geosynchronous satellite has an altitude of 35 million meters, okay, which is only 5.6 times the radius of Earth. So although that's actually high for a satellite, some satellites are as low as 300 kilometers, right? And this one here is thousands of kilometers, okay? But despite that, it's only 5.6 times the radius of Earth as compared to 155. Again, because Venus has such a unusually long day, okay? Which has other bearings on the features of Venus. Okay, and then we were also asked for the velocity of the satellite, all right? All right, or maybe we weren't, but I'm gonna solve for it. Okay, so to find the velocity of the satellite, we simply go back to this expression up here, and we can do a few things. We could actually just substitute in the the value that we solved for here, right? The value of r. We could just solve for it directly, or we can solve for it algebraically from this expression. Okay, and here we go. All right, which is equal to that. See, we're kind of expressing it both ways, and let's see what we get. 583 meters per second, right? And I think the reason I went ahead and solved for this when I wrote out the solution was because that's a strikingly slow satellite, right? It's hard to find satellites that are that slow. In comparison, most satellites around Earth are traveling at thousands of meters per second, kilometers per second. And for example, the lower Earth satellites, called low Earth orbit, which is where the International Space Station is, it's traveling at about 6,000 meters per second, 6 kilometers per second, right? Which is 12 times faster than this satellite would be going. Okay, example 2. Let's look at a more typical satellite. We have a satellite that is 5,500 kilograms, has a mass of 5,500 kilograms, okay? It's going to be orbiting Earth and has a period of 6,200 seconds here. And we're asked for the radius of its circular orbit, the magnitude of the gravitational force on it, and its altitude. All right. And by the way, the fact that we're given the mass of the satellite is only useful because we're finding the magnitude of the gravitational force from Earth on that satellite. Notice that the mass of the geosynchronous satellite for Venus wasn't given. It's not needed. Right? All the kinematic expressions like period and velocity, radius of orbit, those are all independent of the mass of the satellite. Very much dependent on the mass of the planet that's being orbited, but independent of the mass of the satellite. Okay? And you should expect that, considering what we saw about universal gravity and how it shows that gravitational acceleration is independent of the mass of the object that's being accelerated. Okay? So we'll use this relationship that we derived, right, from basically in the previous example. It's a convenient way to relate period to radius. All right? And we're going to then go ahead and solve for the radius from it. So we get that same cube root. And we'll plug in what we know, because we know the period of the satellite. We know the gravitational constant. We know the mass of Earth. Okay, looked it up, and it's 5.97 times 10 to the 24 kilograms. And we're dividing by 4 pi squared. And there we go. We get 7.29 times 10 to the 6 meters. All right, so 7.29 million meters. Okay. And if we solve for the gravitational force, we can plug in that distance, and we get 41,200 newtons. Now, this is interesting because how much would this satellite weigh before it's launched? Which is, of course, saying how much it weighs is the same as saying how much gravitational force acts on it. Well, in that case, it'd be 5,500, this would be Fg on the surface, times 9.8 meters per second squared. And that, of course, would equal something about 55,000. Okay? Well, 41,000 is significantly larger. Okay? I mean, well, smaller. 41,000 is significantly smaller than 55,000. That means that this satellite weighs significantly less now that it's up in orbit. Okay? And that's what we'd expect, because gravitational acceleration decreases with distance from the source of the gravitational acceleration. Things get lighter and lighter as the magnitude that the gravitational force is exerting on the object decreases with distance. Okay? And of course, it decreases with the square of distance. Okay? And to find the altitude, we simply find the orbital radius, subtract the radius of Earth. The radius of Earth is 6.37 million meters, all right, or 6,370 kilometers. And there we go. We find out that it's less than 1,000 kilometers by the surface, 922 kilometers. Not considered low Earth orbit, but definitely on the lower side. Right? So that's kind of a typical satellite right there. Right? And by the way, this period of 6,200 seconds, in minutes, that's about 110 minutes. Okay? All right? So it's about 20 minutes longer than the orbital period of a lower satellite, so lower satellite like the International Space Station. And it's not a linear relationship between the two. Okay? Obviously, because I mean there's things raised to the second and third power. All right? We'll leave example 3 for practice, and the last one I want to cover here is example 4. All right? So let's read the parts here. There's a bit to read here. All right. So in a shuttlecraft of a mass of 3,000 kilograms, Captain Janeway orbits a planet of mass 9.5 times 10 to the 25 kilograms. Okay? In a circular orbit of 4.2 times 10 to the 7 meters. Okay? So 42 million meters. What are the period of the orbit? So some basic kind of things we saw before already. The speed of the shuttlecraft. Okay, so that's those ideas we've seen before. This is where it gets different. Okay, so we'll solve for that initial setup. But then something's going to happen. Janeway briefly fires a forward-pointing thruster, reducing her speed by 2%. Just then, what are the speed and the kinetic energy and the gravitational potential energy and the total mechanical energy of the shuttlecraft? Okay, we're going to use those last equations we saw in the key formulas. Okay, the equations that show the relationships between kinetic energy, potential energy, and total energy of a satellite. Okay, and then in part G, what is the semi-major axis of the elliptical orbit now taken by the craft? Okay, and the reason we know it's going to be an elliptical orbit is because she fired her thrusters in a forward-pointing manner. So she didn't transition from one circular orbit to a larger circular orbit, because that would have required an angled thruster. Okay, if force is applied tangential to the circular path, then the result will be an ellipse. Okay, and then H, what is the difference between the period of the original circular orbit and that of the new elliptical orbit? And finally, I, which orbit has the smaller period? Okay, so let's start with the familiar part. Find the period of the orbit of this circular satellite, right, which is Captain Janeway's ship. All right, plug in the numbers. We just got the radius of this imaginary planet, the mass of this imaginary planet, and there we go. Okay, so we get 21,000 seconds, right? Because it's a smaller mass planet, okay, than Earth. That's gonna have a big effect. That's gonna make for these longer periods at comparable distances. Also, it's pretty high up. Okay, so we have a fairly long orbit, 21,000 seconds. Okay, and then we're gonna find the velocity. Here we'll just go ahead and plug in the orbital period that we already solved for. Make things really easy. Circumference over period, and there we have our velocity. All right, our velocity is only 12.3 kilometers per second. All right, not that fast, right? Well, excuse me, it's well, okay, 12.3. I guess it is on the fast side. Okay, because yeah, 12,300. Yeah, no, it is 12.3 kilometers per second. It actually is quite fast. Okay. All right, we're moving right on. Part C. All right, so here we're going to find the final velocity. All right, after a 2% reduction. Okay, well, 2% reduction in this value will give you this one here. All right, so we've reduced the speed just slightly. Okay. All right, looks good. Okay, and then we want to find the new kinetic energy after this 2% reduction in the velocity. So we'll plug in the values here. And we see then this is the final amount of kinetic energy. Okay. And I could have found the kinetic energy by using the, well, let's see, not in this case. No, here I want to do it this way. This is actually very important because notice that I didn't use the kinetic energy expression that I had introduced a moment ago, the one that is a like term with the gravitational potential energy. And in fact, I will show you. Okay, so this kinetic energy expression, I'm not using it right now. The reason is I don't know the radius anymore. When the thrusters were fired tangential to the circular path, we changed this parameter. First of all, we turned it into a semi-major axis rather than a radius. And second of all, we don't know it anymore, right? So we're going to find this new value. It's going to be A now instead of R, okay? But we can find it by using the fact that kinetic energy still is 1/2 mv squared, okay? Yeah, well, it's always 1/2 mv squared. All right, so now we found the new value of kinetic energy. All right, now we're going to find gravitational potential energy, okay? Because this expression here is independent of the form of the orbit. This is true even if it's not an orbit. This is just dependent only on distance, okay? Is not coupled to kinetic energy in any way, okay? So we can find the gravitational potential energy, all right? And notice here I'm using the distance because at the moment that the thrusters fire, it doesn't matter that she's transitioning to elliptical orbit, she is still this far above or away from the center of the planet. Okay, so R at that moment of the thruster firing, or the moment after, is this value. This is how much potential energy there is. Okay, all right, so now we have that many joules, right? Notice that, of course, the gravitational potential energy is negative, the kinetic energy is positive, their sum is negative, which I'll show here. Okay, so we'll add them together. All right, so this is the total mechanical energy of this now elliptical orbiting spacecraft. And now, finally, I'm going to use the expression for the total mechanical energy, but for, of course, an elliptical orbit, the last equation under the key formula page, and just solve for A. All right, and what do I get? Okay, I get this value. Okay, now I know the value of the new orbit. Okay, and I could solve for things about like if you remember ideas of ellipses, we could solve for eccentricity, for example. I'm not asking for that here, and nor do I give you the formula for eccentricity. You won't be required to do that, but to give you an idea of what's happening. Okay, we have a changed orbit. Okay, so last two steps. Now I can solve for the period of that new orbit, all right, and there it is. That's the period of the new orbit. How does that compare to the period of the previous orbit? Well, before it was, right, 21,500 seconds. Now it's 20,300 seconds. Okay, well, it reduced significantly, okay? So indeed, the elliptical orbit has a shorter period, okay? We took energy out of the system, right? We reduced our speed, changed to an elliptical orbit with a shorter period. So what's actually really neat about that is if you had two spacecraft that were side by side in the original orbit that Captain Janeway was in, and one of them fired their thrusters forward, kind of forcing themselves to slow down. You can imagine the two spacecraft side by side, suddenly one of them drifting backwards from the point of view of the other because it's now going slower. But then, a couple hours later, because this is a long period, the spacecraft that appeared to have slowed down will actually catch up with the first one, coming up from behind it, overtaking it. Pretty neat idea, isn't it? Okay, all right, well, thank you so much for watching this lecture on understanding the orbits of satellites in reference to universal gravitation. I hope this lecture has been interesting and informative. Thank you so much for watching.